Okay. All right, can we go?
Go ahead.
All right, cool. Okay, good afternoon, everyone. So after your lunch breaks now, I'm now responsible to give you all this talk on a Friday afternoon, especially. Wow, people are putting me on the spotlight. All right, so today I'm just going to speak to you a little bit about this HPC thing. You all heard about it. You all heard Werner speak about it on the first day. There's big computers that do a lot of stuff. So I'm going to show you just a few things that we've done in our lab here at UJ, just to show you how one can use this in research, right? How we actually make use of the stuff, doing some research. And of course, most of you being postgrads, getting those papers that you need to publish, right? So, now my thing is not functioning. Give me 1 minute. I just want to put my pointer on. Right, so before I start, just a short intro. So before I joined UJ, I was working for the CHPC. Hence the reason I know a lot of the stuff that they do there. So I used to support the computational chemistry and material science users of the CHPC. So I was the one that was installing software packages, making sure they work properly, and then helping people get done with their research and interpreting results and everything else. Right, then when I joined UJ, which was what, just over a year ago, I joined here as a senior lecturer. And I am now currently the chair of the South African Chemical Institute Molecular Modeling Division. And I'm also the chair of the Computational Chemistry and Material Science Special Interest Group at the CHPC. So anything computational, whether it's computational chemistry or computational material science, most likely somewhere along the line, you're going to see my name. So if you have an issue along those lines, you can feel free to contact me. And if there's certain things that I can help with, we'll try and resolve it. Right? We also try and host events every month where I give guest speakers an opportunity to talk about their computational chemistry research. And at the moment, I'm targeting specifically just South Africa and the universities in South Africa so that you guys can benefit. As South African researchers, you can benefit from other work that other people are doing, and you can also then communicate with these people. Right, so to start, we're going to just focus on 2 projects during my talk, right? The first one was done by my MSc student, Blessing Masora. So Blessing's job was to show that this reaction can actually take place. So this was a green chemistry approach of doing the reaction, right? So they're trying to form these quinolines, but they're using greener approaches to do so, right? So basically, remember, green is we want to go steer clear of any solvent that's toxic and that's going to now give up bad chemicals and everything else, right? So this reaction actually is a 2-step reaction, as you can see. You first form this N oxide, and then in the final product, you form what you require. Now it's like, okay, how do we do this computationally? So just like they did here, this is an experiment which was done, and it was proven to work. So we decided, fine, can we do this computationally? So that's exactly what we tried, right? We broke the reaction up into 2 steps. They don't show you that there's obviously a second product being formed. But a computational approach, you need both, right? If you have 2 reactants, you most of the time are forming 2 products. Some cases you do get just 1 product, but most of the time you're going to get some byproduct at least, right? So in this case, we've got our N oxide and we've got something else that was formed. Then you now move on to the next part where you take the N oxide, you react it with something else. And in this case, we end up with 3 products, right? So how do we do all of this? So basically, we made use of a software package called Gaussian when we ran all of these calculations. In this, we perform various different simulations where it includes potential energy scans, transition state verification, and you look at this in the gas phase, in water, and in dichloromethane. So the reason why we use dichloromethane was because one of the reactions that these guys did experimentally, they actually used dichloromethane. They didn't use water throughout, despite the fact that they said this is green. So dichloro is not necessarily considered a green salt, right? So we wanted to show, can this whole thing be done only in water? That was one of the goals. So this is just a different level of theories and basis sets. Those of you that know what this means, great. Those of you that don't, we come do some computational chemistry. I'll explain that a bit. Right, so here, I'm just giving you a few figures, right? So the one that's most of interest is here at the bottom. So what I'm showing here is just timings. Now, as everybody's been going on about this HPC, these very big machines, they're great. They run stuff faster. While that might be true, It doesn't mean that everything you throw on HPC is going to be fast. So these software packages, even though they've been optimized for the environment they're running in. So currently, the CHPC in this case, if you look, these are the CHPC's now nodes, right? Those are the machines that the CHPC has access to. So everything you see at the bottom here is number of cores. So just like you have 8 cores on your computers or laptops or whatever, the CHPC, each machine has 24. Right? So when I go to 48, it means I'm running across 2 machines. 72, 3 machines, and so on. Right? So I ran across all 5 machines. But the exact same calculation for all of these. So all of these lines is exactly the same calculation, just one is the reactant, one's the product, and one's the transition state. And I wanted to look at what does it take time-wise for these simulations to go from start to finish. Now you'll see these times are not very high, right? These are in seconds. So 6,000 to 4,000, it's more or less about a 30-minute game when you go from, say, a single node to 2 nodes. And then it gets less and less as you go down. So what it's telling me here is, when it comes to HPC, in order for your application to actually perform very well, it needs to scale very well. So there should actually be a straight line that goes from here all the way down. Okay, my cursor is not going straight, but you need a straight line that goes from 24 to 120 in order for it to have linear scaling, which then means that your simulation actually getting faster as you give it more and more cores. In this case, it's not the case. Sometimes it's actually getting slower when you throw more cores. So all it's telling me is, okay, I don't need to go so high with my simulations. I actually can get away with less cores and still get done in a reasonable time. And what you also need to remember is this is a national resource, right? So when you submit jobs to this resource, you have to go and compete with every other academic person across this country and across Africa also, because we also support the African countries. So when you submit a job, there's a good likelihood you're going to sit in the queue. And when it comes to queuing, in order for your job to run, there's 2 main things you need to look at. One is the number of cores you're asking for. So the more cores you ask for, you're going to probably queue longer. And the more time, there's something called the wall time, which is how long your job will run on the cluster or how long you think it's going to run before it's finished, right? So that's a guess, typically, at the beginning, until you become good at what you do, then you know you can make better guesses. But initially, if you guess too high a number, you end up sitting there, whereas another guy already ran like 3 jobs before you because he asked for less wall time and he asked for less resources. So to avoid the queuing, I even gave up my half an hour that I was going to gain from running over 48 cores. I literally just used one single node and I ran it with very short wall times because I knew the timings and my simulations were done. And this was at a time where load shedding was still a problem. So the queuing got even worse. So my simulations were getting finished while everybody else was still sitting in the queue. So like, okay, not my problem. I still get the paper. You can sit in the queue all you want, right? So this is how it works. So you need to be smart when it comes to using these resources because you're sharing with other people. So you have to just be smarter than the other people when it comes to running the stuff. Right, so here's a few pictures of what our products look like, right? So we have the one product, which is now, we've got this carboxylic group, and there's your N oxide on the side. And then here's the 3 products that we formed, HCl, the sulfate group, and then our final product, which was the quinoline. So this looks very complicated, but it's not. It's just, the different colors just mean different things, right? So the black is for a gas phase reaction. Then the blue is when we ran it in water, and then the red is when we ran it in dichloromethane. So if you look at these different barriers, you will see. Now, for those of you that don't know, for any chemical reaction to take place, you have to cross a transition state, right? You don't see it in the lab because the transition state is very short-lived. It's literally just comes and goes. But computationally, we can isolate this, right? So we can see what does this state actually look like before it forms your product. So this is what we've seen. And we see, okay, dichloromethane, the reaction happens the quickest because it's got the lowest barrier. Then comes water, then comes gas. But these barrier numbers were a bit too high for us. So we decided, okay, let's see. When you run things with DFT, typically you do get very high barriers. This is a known defect of DFT calculation. So we try to correct for this. We do what's called energy corrections. So by doing it at a higher level of theory, we're then able to correct these energies, and now they look a lot better. So now you're sitting at like 20, but the pattern's still the same. right? So you still have dichloro first, then come water, then come the gas phase, right? But if you look, the difference between the dichloro and the water is not that big. So there's a possibility this first part of the reaction can actually take place in water. We haven't taken things like temperature and stuff into consideration. So those of you that are going to ask me later, no, I didn't do that yet. So that's something we will still look into. That if we maybe ramp up the temperature, will the water reaction actually take place quicker than the dichloro? That's a possibility. Then, of course, we found a greener route for the first reaction anyways. The second reaction we already knew performed better in water. So for the first reaction, this was the transition state. Can you see it dangles between the two bonds that are being broken and formed, basically. That's all a transition state is. It's that section before the bond is made and formed. Right, for the second part of a reaction, again, we did it gas phase, water dichloro. You'll see here the water barrier is slightly lower than the dichloro, which experimentally they did do this in water. We would expect this to happen, right? In this case, we actually found the intermediate. So intermediate is not the product, and neither is it the reactant. It's something in between. And again, very short-lived, so you never see it experimentally. But you can see it via computation, right? And then we also found a very funny phenomenon, which we had to read, or Blessing had to read lots of papers for, to now see, is this possible? Because most transition states are supposed to be higher in energy than the step before. But this is actually called a barrierless transition state, and it is in fact something that does exist. So it's been proven, right? So we're like, okay, great. It's not just new, at least someone else has found something else. But for this particular reaction, we weren't expecting it. So this was something novel, right? And then we found our final product, where again, the different phases. Again, we did a correction for this. And you'll notice in this case, the gas phase one, actually, that barrier didn't change much, even with the energy correction. But we weren't too cared about that. We were worried more about the water and the dichloromethane. And so we found the second reaction, water is actually the one that is more stable. Hence, that's why the experiment worked. Right, so this was just a transition state here. And then another one, because there were two different transition states in this one. Right, that was project one. Now, you'll not know how to efficiently run Gaussian jobs on the CHPC, hopefully. Right, so the next part was by another MSc student of mine, so Vitalis and Bio. We were looking at antimicrobial resistance, right? So a lot of people in our department are doing antimicrobial, but from the water perspective, we're trying to do it from the bio perspective. In terms of the body is building immunity as well. The more and more antiretrovirals that people are taking, there's immunities being built towards some of these things working the way they're supposed to. Right, so we looked at now, okay, what can we target? We're going to look at the NNRTIs, which is your non-nucleoside reverse transcriptase inhibitors. We're going to try and see, can we maybe computationally develop a drug that might be better than the current drugs that are being used? And that was the goal. Right, so we looked at the different drugs that are currently available, and then you can see here's just a list of the different ones. And these are the ones that we focused on primarily when we started the project. So here, the same story, we did have to do a few optimizations and things of these drugs that are currently being used using quantum mechanics. That would be with Gaussian. We then did docking, but here we didn't use the CHPC because our data sets weren't big, right? So when it comes to things like molecular docking from a bio perspective, you need really large data sets for HPC to make a difference. We were working in the hundreds. That's not going to be much. HPC is not going to speed anything up there. So all we did was we just used our local machines. So you see, nice, like flashy lights, just got some gaming machines and we just dumped the jobs on there. So it actually ran quicker there than it ran on the CHPC's one node. So it was like, okay, fine. Let's do the docking here. Only when we get to really intensive stuff will we use the CHPC. Right, then we also ran a QSA model. Again, this was run locally because the data set wasn't extremely large. So QSA, you just basically take different structural relationship activities and you fit this data to something, right, to some activity. Where once we have the molecules predicted, we then redock them and we run what's called molecular dynamics to see, do these potential drugs stay in the active site of the protein that we're focusing on? And if they do, it's got potential to be a good drug. If they don't, back to square one, right? So you can start again. Right, so here we did just the docking. So you'll see the green one is where it exists in a crystal structure. So typically when you get a crystal from the PDB data bank, some of them have these drugs already in them. So we compare that to the computational approach. Computationally is the red one. See, not too far off, right? So you're like, okay, the docking looks like it's working. Okay, let's use the same approach to now do docking of other things that haven't been done before. So these were the different ligands we tried first. These are the ones that are known. And then there's the scores that are given here. So what we did is we took those drugs that are known. We then tried to find other compounds that actually had activity towards the protein we were looking at. And we tried to fit this data against activity. So we used different fitting models, and we found one that actually worked well for our system. And from there, we decided, okay, let's add on other molecules which have the same sort of scaffold as the original drugs, but just a small difference. Maybe we just add an R group somewhere. So that's exactly what we did. We literally just added some R groups to see, can this improve the docking activity of these molecules? And in some cases, they got better when we redock them. Other cases, maybe not so good, but we were like, okay, it's fine. The methodology is okay. Let's just try and fit the known data and see if it can predict this unknown data. That's what we were looking for. Right, so we looked at our optimized ligands, which were the original ones that had some sort of information that we could use, versus our ones which we predicted. And it shows that the prediction actually now looks a bit better than most of the ones that we started, right? So we said, okay, let's check. Does this work or does it? So we ran some MD simulations, and we found that, okay, this is the original versus our one. Not too far off. And in this case, towards the end here, we actually find that the new one that we predicted looks a bit better than the original. So this is a possible drug candidate. We're not saying it is, we're just saying it's plausible that it can be. We have to obviously now look at the synthesis of this compound. How easy would it be to synthesize, and how easy would it then be to develop as a potential drug candidate? Right. So these are the steps that come afterwards. Now again, quickly to HPC, right? As a last thing. So I showed you before timings for HPC when it comes to CPUs. That's normal. CPUs, everybody's got CPUs in the computers. Then we get to the gamers, which use graphics cards, right? Those of you that love to play games using graphics cards, right? So typically, that's what gaming is all about, was the cards. It's no longer the case. Those same cards are now being used for scientific computing. So these MD simulations you now run on these graphics cards that are developed for scientific computing. They don't have any graphical output, so you can't plug in a screen there and say, let me go play a game, because they're not built for those. They're just built for calculating stuff. So in this case, we ran all of our MDs on these things to see what does the performance look like. Now, for those that are not users of CHPC and are going to become users, I will tell you now, you have a limit to the amount of time you get on these cards. There's a 12-hour limit, right? So for every job you submit, you're allowed to use it for 12 hours before the wall time runs out. Most of these simulations you can restart, so it's fine. You just continue from where you last stopped. But now, let's look at the first one. If you're running a simulation that's only giving you 115 nanoseconds a day, right? Typically, the software packages print out how many nanoseconds they're giving you in a day. You run this at 115 per day. You're like, okay, great. That thing's giving me 115. I'm going to submit my 12-hour job for 100 nanoseconds. Do you think you're going to get your 100 nanoseconds up? Because in 12 hours, you're only getting 57 nanoseconds. You're not getting 115. You're getting 115 in 24 hours. So you need to make sure you take that number, divide it by 2 to get the amount of time you're going to get within 12 hours. So if you were to try and run that 100 nanosecond, what will happen is your simulation might die at 57. But if you didn't set your software up properly, and a lot of cases, people use a software package called Schrödinger. If you ask for 100, it doesn't write a restart file until it reaches that 100. So you start a simulation from the beginning again and go queue again and do the whole process again. So avoid the problems. Rather cut it down and make sure you run for like 50 nanosecond gaps in this case, so that you get a restart file that you can then add on to give you. 250s will give you 100, finish. And you can then just put the stuff together, right? So you have to be very careful with these simulations so that you don't end up now using the resources and then using it for the same job again and again, because now you fail to see this was the story. Right, so just quick conclusion. you don't need the greatest number of cores, right? And the highest available wall time in order to run your simulations, as you'll have seen. And you must always test to see what's optimal on an HPC environment, especially since you're competing with other people, right? You're competing for resources. So rather do it properly so that you get in before everybody else. And the short gain you might obtain in simulation time, you will lose in queuing if you decide to now not do things properly. You don't need to use the CHPC for every simulation, as I've proven. You can use your local machine. Some things run quickly. You don't need the CHPC. All of you guys here have written Python programs. Do you think if you take those Python programs that you wrote now and you put it on the CHPC, it's going to run faster? Just a quick question. You can even Slack me there. I'll look at your answers afterwards. Anyone in the room here? Okay, so I hear no. And that's correct, because if you look at these Python programs you'll have been writing, is there anywhere where you actually see anything about cores or processing in parallel or something along those lines? No, right? Everything's using one single core. So even if you put it on the CHPC cluster and you ask for 24, you're only going to use one. So you have to now make sure the code is parallelized in order for it to use more cores. Right, and then we are aware that CHPC will be upgrading its resources. They're supposed to this year. We will see, let's hope. But when that happens, more resources means more misuse. So I urge everybody, the online guys, the other campuses, everyone, make proper use of HPC. Don't just submit a job to submit a job. And then, as I said, end up in situations where I've had cases where people ask for like 140 calls, but they're using one. Now the other resources stand there waiting for you to do something with them, but they get nothing. And then other people could have used that instead. So please, just use it. Use it with care and caution. And think about other people. And as a final thank you to my students, my collaborator, the Department of Chemical Sciences, and then Nikki's and Nitix for allowing me to speak.
Thanks so much, Krishna, for that talk. Hopefully everybody get an idea of the type of work that you do. There was a question from Rahul saying, in computational chemistry, do you simulate chemical reactions? If so, how do you do it?
Okay, so the first project that I showed there, that was a chemical reaction. So we simulated that whole reaction from start to finish. And in that case, we did it with conventional quantum mechanical methods.
Okay, thanks, Krishna. We'll try and get your notes as well on Canvas, and then also the recording later on. Thank you so much.
All right, no problem.
Okay, so this is the last part of Friday, so we actually won't be spending too much time to do the last part. So let me just stop this recording and